Welcome to lesson 2 from chapter 8, year 2 pure mathematics. This is all about parametric equations. Today we're going to be converting parametric equations into Cartesian form, okay, but this time we're going to be using trigonometric identities. So it's a good idea as preparation for this lesson to go over your trig identities, firstly from year 1 and then from year 2 in chapters 6 and 7. If you're ready to proceed, please pause the video and try the 4 warm-up questions. Okay, and let's have a look at the solutions. So you'll notice in question 1, we're given the parameters x equals cos t and y is equal to sine t. The parameter is, of course, t. There's no range of values of t. This is not strictly a parameter question. It's just an exercise in hopefully producing an identity. And it says in the question to use a suitable identity. So we have to rack our brains and think, is there an identity that allows us to write down an equation purely in terms of x and y only? So is there an identity that links cosine and sine and nothing else? Well, if we think back to year 1, there was an identity we used very regularly that does indeed link the two together. And I'm going to write it down like this. So it's going to be cos squared t plus sine squared t is identical to 1. And remember, of course, it doesn't matter what variable you use. This is true for all values of t, okay, or theta, or x, or whatever else you choose to use as your variable. In this instance, we're using t. So clearly, cos squared t would be equal to x squared in this instance. So we can simply write down the equation now as x squared plus y squared is equal to 1. Notice I've dropped the identity because we are specifying in this situation that cos t is equal to x and sine t is equal to y, not identical to. So the more or less varied or less, what's the word, less strict identity component has to go, if that makes sense. It's only equal to in this instance because it's not necessarily true in all cases. Right, so for part B, it says state the properties of the curve C described by the equations given in part A. Well, if you look at the equation, I'm hoping you'll recognize it, and we can write down all the properties that are attributed to this equation. So I'm hoping you recognize that this is indeed a circle. All right, and if we write down the properties, well, we can write down its property as the center, so it would be a circle. Let's write it down properly. Circle, center at the origin. All right, because there's no translation in the x or y direction. And also the radius corresponds to the right-hand side. If you remember, of course, that this is r squared over here, the radius squared, so the radius must be 1 unit. Okay, so I hope that makes sense. And moving on to question 2 now. Now we've established how we can use identities, that kind of form. We're going to have a look at the range of values that we can possibly have. Now, we've only got one variable here. We've got x written in the parameter t. So if you look at the range of values of t that we can actually input into this, it's a full circle, excluding the excluding 2 pi, but it would cover a full circle when 0 is included. And it says state the range of values of x. Well, if we can plug in any value of t between 0 and 2 pi, I'm just going to remind you of the sine curve, because we're dealing with x and it has the sine function as part of it on the right hand side. We just think about the sine function for a second between 0 and 2 pi. it completes one full period, and we have the nodes at 0, pi, and 2 pi, like that. So this would be y equals sine x, or something like that, if this is the x-axis and this is the y-axis. Okay, now as you'll know from hopefully from the work you've done so far, we have maximum values at 1. Okay, it maxes out at 1. It's never ever going to exceed that value, and it also has a minimum value at -1 within that range. Now, obviously, if we restrict that range, that might not necessarily be the case. If we restrict the range between 0 and pi, for example, so when I say the range, sorry, the domain between 0 and pi, the range you will get would just be simply between 0 and 1. So you have to be careful with the domain you've been given, or the range of values of t, or whatever the parameter is that you've been given. So that's really important. So because we're using 0 to 2 pi, we can see that we're going to have all values between -1 and 1. So how does this help us write down the maximum and minimum values, and or the range of values, because the hint just does say to use the maximum and minimum values of x. Well, if we look at the sine t part, the sine t is limited between -1 and 1, as we can see from the diagram we've just drawn. So I can write down my maximum value for x. I'll call that x max, and that would be equal to 2 plus 3 lots of, and the maximum value you can get for sine within that domain, or within that range of values of t, I should say, is 1. Okay, so just tidying up that's just going to give us 5 altogether. Now, for the minimum value, x min, this is going to be 2 plus 3 lots of the minimum value you can possibly get for sine t, again using this range of values of t. So that's going to be -1. And again, tidying all that up, that's going to be 2 subtract 3, which is, of course, -1. So now we've established what x max and x min are, we can now say the range of values of x as between -1, inclusive, of course, and 5. So I hope that makes sense. So that's the range of x, okay, as requested. Now, question 3, we have an x variable defined in terms of t. Nothing said about parameters in this instance, but what we have to do is use a suitable identity again. Notice that phraseology that we have here, suitable identity. So we have to think of an identity, excuse me, that is suitable, to rewrite this, and we have to write it in this harmonic form. Now, this harps back to chapter 7, when we're looking at harmonic trigonometric functions. So is there a way we can break apart this sine function here to write it as a linear combination of sine and cosine? Well, yes, we can. I'm going to go back to what's in the formula booklet, and everything is there that you need in this instance. And we're going to use the compound angle formula for a subtract b and taking the sine of it. So we're going to use the sine of a subtract b, which is identical to sine a cos b subtract cos a sine b. Just making sure you get the signs, as in the plus or minus parts, correct. So that would be taken from the formula booklet. You wouldn't have to learn that, although it is handy if you do know them, because you'll find that they're easier to use, and things will jump out at you more when you're trying to solve problems. Okay, so let's see what we need to substitute in here. Well, clearly we've got to replace the A and the B right here. So the A is going to be the t part, and B is going to be pi over 4. So I'll just write that out a bit more formally. So A is equal to t, and B is equal to pi over 4. Obviously, this is obviously in radians. And let's substitute all this into the formula. So sine all the way across as well of t subtract pi over 4, which is equal to x, of course, is identical to sine t cosine of pi over 4 subtract cosine t sine of pi over 4. So that's that. Now, what we have here is we've got a coefficient of sine t, which is a number we can write in a slightly different way. And we've also got another coefficient here, which again is just a number, constant in fact, so they will correspond to the A and B stated in the question. So let's do that. So all this of course is equal to x, so I might as well say, well, x will be equal to whatever I have on the right hand side. Now, if you don't know what the cosine and sine of pi over 4 are, they are standard results. If I just do a little sketch up here, you can use your calculator for this if you like, but pi over 4 is of course 45 degrees. So if that angle there was pi over 4, this angle here must also be pi over 4 because it's 45. It's a right angle triangle because we're using trig, aren't we? And this is also isosceles, so it's a right angled isosceles triangle. And what we do in this instance is we set the two short sides that are equal in length to 1, which gives you a hypotenuse of length root 2. And then it doesn't matter which angle you choose to use. If you decide to use the angle at the bottom here, okay, if I take the cosine of that, it's just going to be 1 over root 2, which is the same as root 2 over 2. Okay, and your calculator will probably give you root 2 over 2 straight away anyway. So this is going to be root 2 over 2 sine t. And if you take the sine of pi over 4, it's exactly the same because it's isosceles. So that's going to be subtract root 2 over 2 cos t. All right, and they obviously correspond to the A and the B, as I've just said, but B is negative. That doesn't matter. So we'll just write down what A and B are. So therefore, A would be root 2 over 2, and B would be negative. It would be negative root 2 over 2. So there we have it. So that's what X would be in harmonic form. Now, moving on to question 4. This is an interesting question. We have cos squared of t is equal to 3/4, and we have a very restricted range of values of t here between negative pi over 2 and pi over 2. So negative 90 degrees and 90 degrees. And it asks us to find the value of cos t. All right. Now then, if this was a trig equation, you just go straight into it. Let's find cos t, principal angle, and solve. We're going to do a bit of that, but then we're going to sort of halt and then just discuss what cos t might actually be with this restriction. So I'm going to take square roots of both sides here. So therefore, cos t would equal the square root of both sides. Now, obviously, you can have plus or minus root 3 over 2. And you might think, well, that's the answer, surely. But it says specifically in the question to find the value, okay, as in singular. So not plural. I've got two answers here, but I want just the value. So we could split this up into two questions, and maybe one of them will be completely redundant. So let's consider cos t is equal to the positive version first, so that's √3/2. Now, if this was, like I said, if this was a trig question, you would find your principal angle, and then you would stick it on your cast diagram. Now, I don't really actually care what the principal angle would be pi/6 because it's √3/2. But I'm not actually interested in what it is. It's just a case of whether it's valid or not in this instance. So if I draw the cast diagram and we write C, A, S, and T, because this √3/2 is a positive value, okay, my principal angle, whatever that might be, even though we know it's pi/6, if you just work it out, would have to go in A and C. So I would just put those on there. So there would be A there and C there. So that those would be the two angles. And it doesn't matter what the angle is, but it would be T, won't it? Whatever it is, it doesn't really matter what it is. And that domain that I'm interested in runs from -pi/2, which is here, up to pi/2, which is there, and then 0 is there, and the positive direction is obviously that way. So we can see we have two possible answers, okay, which is fine. So we know this is valid. There's nothing wrong with this. Cos t is valid in that domain. We would generate two values of t. Now, if we take the alternative, so if I just very quickly consider cos of t would equal -√3/2. You might have spotted where this is going already. If that was negative, now if I just highlight that, because this is negative here, it would have to go into the negative quadrants. Okay, the principal angle would be the same because you ignore the negative sign when you're working out the principal angle, but the value of your principal angle would have to go into the negative quadrants. Now, the negative quadrants are outside of the range of values of t that you're working in. We're only interested between -pi/2 and pi/2, and we're working that way. So these two quadrants here and here are irrelevant. They fall outside of my values of t that were prescribed in the question. So this cannot happen. So this is invalid because of the restriction. So the only value of cos t that we're allowed is the √3/2 and the positive version. Okay, so I hope that makes sense. It's subtle, but it does bring together all those pieces of knowledge that we learned in chapters 6 and 7, and possibly in year 1 as well. Okay, so next we're going to move on to the worked examples, working with parametric equations and trig identities. So looking at the worked examples, there's a little bit of an introduction to this, just to get you thinking. It says that you can use trig identities to convert trigonometric parametric equations, there's a bit of a mouthful, into Cartesian equations. Yes, we kind of established that in the warm-up. And it says you can expect to use Pythagorean identities, compound angle identities, or the double angle identities. So it's all the work that we've covered in chapters 6 and 7 of the pure maths. So the first worked example, it states that we have a curve C with the parametric equations described. So as is customary, I'm just going to call this one equation 1, this one equation 2, just so we know what we're talking about. And we're asked to find a Cartesian equation of the curve. Now, when we're dealing with trigonometric parametric equations, it's not a good idea to make t the subject. T itself, the subject, is tied, t itself is tied into the trig function. So it's like a sine t or a cos t or a tan t perhaps. So that's not a good idea. What is a good idea is to make the sine t or the cos t, the subject first. So that's what we're going to do. We'll take some notes while we're doing this. So for part A, so in equation 1, we're going to make sine t the subject. Otherwise, you would have arc sines and things like that everywhere, which would be rather cumbersome. Okay, so we're going to make sine t the subject. Now, that's really easy. We only have to add 1 to both sides. So therefore, x plus 1 is equal to sine t. Okay, and we repeat this with equation 2. So also, in 2, we're going to make cos t the subject. Then we can let the identities do the work. All right, so again, that's really simple. I just have to subtract 4 from both sides. So we're going to have y subtract 4 is equal to cos of t. Now that we've done that, we've got sine t and cos t are in play. We need to think of an identity that links together both sine t and cos t and nothing else. Okay, so you might be thinking sine t over cos t is tan t. Well, that's no good because that brings tan into it. We just need sine t and cos t. And this is where we use the Pythagorean identity from last year, okay, from year 1. So we're going to use, if you haven't thought of that already, sine squared t, we'll use the same variable, plus cos squared t is identical to 1. Now that we have that, we just have to square our expressions for sine t and cos t, and we set them equal to 1. Okay, the identity loses that true for all t because we are specifying that sine t is equal to x plus 1, not identical to it. Just to make that hopefully clear. So sine squared, of course, is going to be x plus 1 all squared. Okay, and then we add cos squared, which is, of course, y minus 4 all squared, which is going to be equal to 1. There we have our Cartesian equation. Not asked to make y the subject, so we can leave it like that. And what's great about this is it's presented to us in a way that tells us lots and lots about the curve itself. Okay, so this is the curve C. Now, what do we know about C? Well, the form suggests that it's a circle. Hope you spotted that. Okay, and then we can also write down some of its properties. Well, we know that it has the center. Now, the center of the circle is dictated by these values here. So we've got the plus 1 there and the negative 4 there. We just simply have to change the signs of those. And then we've got the coordinates of the center of the circle. So that's going to be at negative 1 and 4. Okay, and then the radius of the circle on the right-hand side is the square root of that number there. So that's, of course, going to be 1. So just write that down. Okay, so those are the key properties. Now that we've got that, we can sketch the circle. So this is for part B. So we have to make a sketch of this circle. All right, so let's just be mindful of what this actually looks like. We've got a center at negative 1, 4. So we can put that on. I'm just going to put the axes on first. So negative 1, 4 is in the top left quadrant. So put y there. There's the origin. And there's x. Now, negative 1, I'll put that on here. Okay, 4 will be up here somewhere. So that's where my center is going. Now, this is where you got to sketch it carefully. Okay, you have to be clear about, you know, where the radius intersects the coordinate axes and things like that. Now, as you can see, if the radius is 1 unit, as we can see here, we've just established that, my center is 1 unit from the y-axis. Okay, so that means my radius is 1 unit from the y-axis also. So when I sketch my circle, which I'm going to do now, it must be touching the y-axis. So the y-axis is tangential to my circle. So it's going to do this. Okay. And how could we verify this? Well, you could check this, because if you put in, obviously for the y-intercept, if you set x equal to 0, rearrange the equation, you're going to get the y value as 4. Okay, but you can check that yourself. So this would be the circle or sketch. So we can label it as x plus 1 squared plus y subtract 4 squared is equal to 1. Okay, and this is the circle C. All right, so there's our first parametric equation in terms of trig functions. We've got a circle. So let's see what else we can generate using variations of this. Now, for example 2, I've already labeled the equations. We're given x and y in terms of sine and cosine, again, respectively. We have to find a Cartesian equation of the curve C. C is described by these parametric equations. This time, just being very conscious of the question itself, we have to write it in the form y equals f of x. So y has to be the subject. And we've also got a range of values of x. So this would be the domain of f, as we said in lesson 1. And k is a constant to be found. All right, so the domain differs by 2 units. So, and then for part B, we also have to find the range of f of x. So we'll do that obviously second. So for the Cartesian equation, let's make a note. This is part A. Once again, I'm not going to make notes here. We'll just do it. We're going to make sine t the subject, first of all. And then we're going to make cos squared t the subject. So in 1, we're going to have x plus 1 is equal to sine t, just simply adding 1 to both sides. In equation 2, we have y subtract 4 equals cos squared t. So you'll notice the difference here. It's not cos t, it's cos squared t. T can be any real value as well. So we'll just have to bear that in mind. Now, when we are finding our Cartesian equation, once again, we look at what we've got here. We've got sine t as a subject here. We've got cos squared t as a subject there. We need an identity that links sine and cosine together and nothing else. We're going to use exactly the same identity as example 1. So we're going to use sine squared t plus cos squared t is identical to 1. And now we can make the substitutions and set up our Cartesian equation. So sine squared, I'm going to have to square this expression for sine t there. So I'm going to have to square that. So we're going to have x plus 1 squared. Now, this is where we've got to be a bit careful. We already have cos squared. It's squared already. So we can replace cos squared with y subtract 4. So that's going to be plus the y subtract 4, which represents cos squared. And all that is going to be equal to 1. Now then, we're told to make y the subject. So we'll make a note. So make y the subject. because we're asked to do so. Now, this case, the first thing I'm going to do is I'm going to add 4 to both sides. So therefore, we're going to have x plus 1 squared plus y. If I add 4 to both sides, that clears the 4 on the left, but I'm going to have 5 on the right-hand side. And then I can subtract the x plus 1 squared. So therefore, y is going to equal 5 subtract x plus 1 all squared. Now, what's extraordinary is because we had the cos squared in the parametric equation for y, it's changed the curve entirely. We now have a quadratic. So we have a parabola which has a maximum, and it's written in completed squared form, which is really, really handy as well. All right, now what we need to do is to determine what this domain of y is. Well, what do we know? We could determine the domain from looking at the curve, but we don't know much about it because we were given t as our parameter right here, and we're told that t is any real number. So it's a good idea if you're working out the range of values of x, in other words, the domain of y, which is f of x. It's a good idea to go back to the original parametric equation and try and determine what the domain is from that. And this goes back to what we did in the warm-up questions. So if we consider how sine of t behaves for any real number, we know it oscillates between -1 and 1. So it has maximum values and minimum values. So we know that sine is trapped between -1 and 1 for all real values of t, so for all real t. In other words, what I mean is t is a real number. Okay, that is a true statement, isn't it? So if I do sine t subtract 1, so therefore, if I subtract 1 from both sides, that's going to be -2 sine t subtract 1, and then I have to subtract 1 from the other side, that's 0. And then we know from how it's defined in the question that sine t subtract 1, I didn't just put that out of thin air, that is of course how x is defined, so we know that's the same as x. So therefore we've got -2 x and 0, okay? And x is sandwiched between -2 and 0. This means, of course, that this would be -2 and this will be 0. So in other words, k is equal to 0, which we've just deduced. All right, so I hope that's okay. It's actually quite nice to work out the domains and ranges when it's given in trig form, because you just have to know the maxima and minima of sine and cosine, essentially, which you know pretty well. Now for part B, we need to determine the range of f of x. So this is going to be a similar exercise. So for part B, we're going to consider for the range that remember the range is the y values. So we're going to use y equals cos squared t plus 4, and t is any real number. So we've just got to figure out what would be the range of values of y for this. Well, if we think about cosine, what do we know? So we know that cosine, exactly the same as sine, is sandwiched, trapped, if you like, between -1 and 1. Those are its minima and maxima, respectively. Okay, repeating for infinity. Now, if we square it, well, we could square the whole thing, but we would get a kind of a nonsense statement. We would just get that the cosine of t is just 1, essentially, which can't be true. But we know that because the cosine, if I just draw it a little bit, runs like this. So it's just a shift of sign. Because it runs like that, by squaring it, all the numbers that are less than 1, and it doesn't matter if they're positive or negative at this stage, but all those numbers that I've just highlighted there in green, they're all fractions essentially. They're numbers between 0 and 1. And when I square them, they get smaller, okay? But they also remain positive. Now, the numbers on this side, which correspond to all these values, they're also between 0 and -1. And when I square them, they, of course, become smaller, but they also become positive. So we know that's cos squared, however it looks, is going to be sandwiched between 0 and 1. I hope that makes logical sense based on what I've just said. So when we've got that in place, we can now apply the transformation and see what happens to get our range. So for the y value, we need to add 4 to this. I like putting the therefores as 3 dots. I hope that's all right. So if I add 4 to both sides, we get cos squared t plus 4, which is less than or equal to 5, just adding 4. And again, that wasn't arbitrary. I've done that for a reason, because the cos squared t plus 4 is exactly the same as y. So I'll not put therefore this time. So 4, y, and 5. So the range of values are between 4 and 5 inclusive. Okay, so that's the range of f of x, y being f of x, of course. Okay, moving on to question 3, or example 3, I should say. We've got more parametric equations. Notice there is a subtle difference again. We now have cos of 2t, not cos squared this time. And we have to find a Cartesian equation of c in the form y equals f of x. That's our first job. And notice, of course, the range of values of t are between 0 and 2 pi. So that's one full circle. All right, so we'll just apply our methodology that we've been using already. So for part A, we're going to make sine t the subject in equation 1. So in equation 1, we have that x plus 1 would equal sine t, just by adding 1 to both sides. And in equation 2, we have that y subtract 4 would equal cos of 2t. Right, there's nothing else we can do at this stage. That's it in terms of rearranging the equations. And please note that says in equation 1, not ln, in case you were wondering. Now, looking at the right-hand sides of these rearranged equations, we have sine t and we have cos of 2t. Now, we have to think of an identity that links both of those things together. Well, there is a clue, of course. We've got cos of 2t. Now, there are 3 variations of the cosine double angle identity. And the one we want has to contain the sine t. So we're going to use cos of 2t is identical to 1 subtract 2 sine squared t. Okay, because that's the one identity that contains both of those elements that we have to have. So this is rather good. So this means that in that identity, I can just replace the sine t with x plus 1 and the cos of 2t with y subtract 4. So let's do that. So on the left-hand side, we're going to have y subtract 4. I think that deserves a therefore. Is equal to 1 subtract 2 lots of. Now, sine squared t, I've got to square the x plus 1. So it's got to be x plus 1 all squared. Like that. And it asks us for c in the form y equals f of x. That's no problem. I just have to add 4 to both sides. So y is going to equal, if I add 4, that's going to be 5, subtract 2 lots of x plus 1 all squared. And once again, we have a quadratic, a parabola. Great. So that's the Cartesian form done. Now, for part B, we're asked to state the domain of f of x. Right. Again, for domains and ranges, it's a really good idea to go back to the original parametric equations. So for part B, I'm just going to write this down. Obviously, the domain of f of x is the x values, isn't it? So that's what the domain means. So we need to consider the range of values of x equal to sine t subtract 1. And the range of values of t may play a part here. So t is value between 0 and 2 pi. Well, between 0 and 2 pi, sine has a maximum and a minimum. Okay, so that's fine. So we know that sine t will be sandwiched between -1 and 1 for that range of values of t. And if we subtract 1 from both of those, we're going to have -2 sine t subtract 1, and then subtract 1 from the right-hand side of that inequality, which is 0. And just once again, just to remind you, I've subtracted 1 because that's what x, or that's how x is defined. Okay, so that's got us the domain. So the domain would be from -2 up to and including -2 up to and including 0. So that's quite interesting. So if we want to sketch this, there's a few things which we're going to have to consider when we're doing it. We're also asked to state the range of f of x as well. Now we could actually do that now before we actually do the sketch, just to help us make our sketch a bit more realistic. So if we look at the y values, these are going to be the range. So the range of f of x. Now, once again, we've got cosine of 2t. The cosine 2t, remember the two inside the function is a horizontal transformation. It just changes the period, essentially. So it does nothing to the range of values. The range is still going to be between -1 and 1. So we know that cosine of 2t is going to be between -1 and 1. Okay, you can check this you can do some Desmos or GeoGebra plotting if you're not convinced. Just plot the graph of y equals cos 2x between 0 and 2 pi and just check that you get the minimum and maximum at -1 and 1 respectively. So by adding 4 to both sides, we're going to have, just write that as an instruction. If we add 4 to all this, we're going to get 3, of course, cos of 2t plus 4, and then 5 on the right-hand side. And as you know, the cos of 2t plus 4 is because this is what y is, so this will give us the range as well. So we're going to have 3 up to 5. So this is the range. Now, for our plotting, let's draw some axes. So the x values, the domain is going from -2 to 0. So it's only on the left-hand side, and it's the upper quadrant. So it's going to be from 3 to 5. Like that. So I'll just put those on. So just plan ahead when you're doing your sketching. I'm as guilty as anybody of this, but so 0. So from -2 up to 0. So we'll put those on. So put -2 about here. 0 is already on there. That's the origin. So that's my domain sort of mapped out already. So here it is. So I'm just going to, that corresponds to those values there that we found earlier. And then the range will be from 3 up to 5. So 3 to 5 will be somewhere up here. We'll put them on. We might have to change them a little bit. We'll see. So from 3 up to 5, so that's the range. So I've got to put my curve on here. Now, to get this right, we need to figure out where the mirror line would be. Now, if we go back to the function, the Cartesian form that we found earlier, which is right here, there's lots of interesting information in here. We can see because this is a quadratic, it's going to have a negative x squared. So that tells us that it's going to have a maximum. The maximum, of course, is going to be at 5 because that's what the range tells us from what we deduced earlier right here. And also from this number here, it tells us explicitly that the maximum is 5. The mirror line, the line of symmetry, if you set the x plus 1 equal to 0, that's going to give us a mirror line at -1, which would be right here. So that's where your mirror line is. So we know it's symmetrical about there. So that means that if I put in -2 for my x value, I'm expecting to get 3 here because it should be symmetrical. So let's just test it. Let's see what the y value is. When x is equal to -2, which is the first value in my domain, y is going to be 5 subtract 2 lots of, now -2 plus 1 is of course -1, and we've got to square all that, which is essentially 5 subtract 2 lots of 1, which is 2, which is of course 3. So my first coordinate, if you like, would be right there at -2, 3. If I put in 0, let's see, we should get the same value. So y would be equal to 5 subtract 2 lots of, now that would be 0 plus 1, which is 1 all squared, which equals 5 subtract 2, which again is 3. Great. So we now know that we have a point there. So we can quite happily put the maximum at -1, 5, and our parabola is going to, I'm just going to make that a different color. It's going to pass up to there and back down like that. Okay, so it was quite helpful to find the range earlier, which we did. Okay, so I hope that makes sense. That was example 3. Let's see what we've got to do next. All right, so number 4 looks fairly innocuous. I've labeled the 2 equations 1 and 2 for x and y respectively. And we have to find a Cartesian equation once again with y as the subject. So we'll go straight to our methodology again. So for part A, so we have x equals 2 sine t. So I'm just going to divide both sides by 2. So we have x over 2 is equal to sine t. Okay, so that was from equation 1. And for equation 2, nothing else we can do here. It's already the subject. Now we're stuck with y is equal to sine 2t. So we have to think of a trig identity that we know really well that links together sine t and sine of 2t. Well, we only have one option. And our only option is the double angle identity for sine. Now, we're going to use sine of 2t is identical to 2 sine t cos t, like that. We have to use that. We've got no other choice because we have sine 2t. Now, this, as you can probably tell he's going to throw up a problem. I'm going to substitute in as best I can. So I know that I can replace the sine t here with x over 2. So I'm going to do that. And we can call sine 2t obviously y. So again, so y is going to equal 2 lots of, now the sine t will be replaced by the x over 2. So I'll just put that in. Okay. Good news is we get the 2's cancelling out, multiplied by the cosine of t. So therefore, just to finish off this little bit, y is going to equal x cos t. Now, if you left it like that, that would obviously be wrong. The key problem here, as you may be able to tell, is that we have 2 variables on the right-hand side. So we've got y defined in terms of x and our parameter t. That's not what we want. It has to be purely in terms of x. So we scratch our heads and think, what on earth are we going to do with this? I've got to somehow find an expression for cos t purely in terms of x. So let's go back to our first equation that I've rearranged right here. Can we do something with this? So we now have to ask ourselves, because we have cos t appearing, is there an identity that links cos t and sine t together and nothing else? Well, we've asked this question already several times. So we're now going to use the one that we know really well. Sine squared t plus cos squared t is identical to 1. Because that's the only identity that links cos and sine together and nothing else. And we're forced to do that by the situation we're in. Now, sine squared t is, of course, going to be x squared over 4, okay, by squaring this expression here. So x squared over 4 replaces sine squared t. Now, we add the cos squared t, and because I've made that substitution, which is equal, not identical, this must be equal to 1. I can now make cos squared the subject. So therefore, cos squared t is now going to be equal to 1 subtract x squared over 4. Okay. And let's bring this up to the right-hand side. So let's carry on working up here, and let's see what we can do with this. We've got to be careful, right, throughout all of this, because we have a very specific restricted domain for x and for y, governed by this range of values of t. Now, if we just think about this for a minute on a cast diagram, what would that actually tell us? Well, on a cast diagram, we would have, I'll just draw it. So C, A, S, and T. Now, the T values run from pi over 2 to 3 pi over 2. So pi over 2 is, of course, here. Obviously, we start at 0 and we go anti-clockwise in the positive direction. And 3 pi over 2 would be here. So difference of pi between them. So that means that if we're going in this domain here, we're only allowed to have values between pi over 2 and 3 pi over 2. This is the S and T quadrants. Okay, so S quadrant and T quadrant. So we'll come back to that in a second. What happens then to our cos squared t? Well, I can't leave it like that because I need to put cos t back in. So I have to square root this. So let's square root it. Now, the problem arises that when I square root, there's 2 possible solutions. There is the positive root and the negative root. Okay, and it's going to be 1 subtract x squared over 4 like that, all square rooted. But is this correct? which one do I substitute in? I've got two possible answers. Do I use both or do I just use one? Well, this is where we go back to the range of values for t. Okay. Now, if we look at the range of values for t, I've already said that the t values will lie in the s and t quadrants. Now, more specifically, what do we know about the s and t quadrants? We know that cosine is negative in both of these quadrants, which means that my cosine value has to be a negative value. It has to be. Cosine is negative in those two quadrants. Cosine will be always negative for all of those angles between pi over 2 and 3 pi over 2. You just have to sketch the graph for you to see that. Now, if that's the case, because when I take a square root, I'm forced then to select the negative root because I have to have a negative value for cosine. Okay, and this goes back to what we stated in the warm-up question 4. So we'll just make a statement, okay? So since t is bounded between pi over 2 inclusive and 3 pi over 2, we've now deduced that cos t must be negative, and we have an expression for it as 1 subtract x squared over 4 all square rooted, if I hadn't said that already. Okay, that means that it's got to be negative. Right, now we can substitute this back into our semi-Cartesian equation that we had earlier. So therefore, going back to the result earlier, just going to going back to this, I should say. Okay, we now know that y is going to equal negative, so I'll put the negative at the front, x multiplied by the square root of 1 subtract x squared over 4. Now, obviously, I could have changed the question. If I'd have said that the values of t were between, let's say, for example, negative pi over 2 and pi over 2, cosine would have indeed be positive, so we wouldn't have the negative sign in there. But because of the range of values of t, that dictated that we had to take, so that range of values dictates that this has to be negative. I hope that was clear. I'll show you this on GeoGebra after we've finished the example. So for part B, we have to state the domain and range for f of x. All right. Well, let's just have a look at this. We're going to have to look carefully at this restriction. For the sine graph, I'm just going to again sketch the sine graph here. I'll use brown for a bit of variation. So between pi over 2 and 2, I'm just going to sketch the sine graph as we know it a bit more commonly. So sine between 0 and 2 pi looks like this. We'll put those numbers on. So we've got 0, pi over 2 at the maximum, pi there at the node, 3 pi over 2, and 2 pi. And this would be y equals sine x, for example, or sine t, or whatever, it doesn't matter. Now then, if this is the case, and we might as well do this properly. So if we look at that, if we're interested in t values between pi over 2 and 3 pi over 2, then it would be equivalent to using this domain here. So it would be between pi over 2 and 3 pi over 2. So it would be all those x values there. Now, those x values would have corresponding y values between 1, which is the maximum because pi over 2 is included, and 3 pi over 2, which is the minimum, which is also included. So for that range of values of t, we know that sine t is going to include the maximum value and the minimum value. We just needed to check that because when you restrict domains, it can change the range quite drastically. So for pi over 2 up to 3 pi over 2 as values of t, we know that sine t is bounded between -1 and 1. And if that's the case, just by doubling everything, therefore multiplying everything by 2 will give us this. And the reason I've multiplied everything by 2, of course, is because we have 2 sine t there, 2 sine t here, which corresponds to x. So therefore, -2 up to and including 2 is our domain. Right, okay, so that's that done. We've got our domain, which is great. Another thing we have to find is the range. So now we're going to work on the second equation here. Now, sine 2t, because we've got the 2 inside, you could sketch this. In fact, I will do. I'll sketch on the same axes. It doubles the period, essentially, because it's inside the function. So, for example, if I put in pi over 2 for my t value, it's going to return the same value as it would for pi, okay, which would be there. If I put in pi over 4, it would return the same pi value, the same t value as I would for pi over 2, which is the maximum. So you can see it's compressed. It's a scale factor of 1/2 in the horizontal direction. So to sketch the graph, it's going to complete 2 cycles like so. So this would be y equals sine of 2x on my sketch. Now, you'll notice as well, this confirms, or it's further confirmation that you're going to be oscillating between pi over 2 and 3 pi over 2, which also incorporates the maximum and the minimum values. So there's nothing to worry about there. So that means that for my range, because I know that sine 2t is bounded between -1 and 1 in that same range of values for t, because I've just been talking about that. That means, of course, that y would be bounded between -1 and 1. Okay, so that would give me my range of values as well. So a few sketches here and there do make all the difference, you know, when you're trying to deduce what the domains and ranges are. Okay, so that concludes example 4. Okay, now just before we move over to example 5, just want to show you using GeoGebra the result that we've just looked at. So the black curve here that you can see is the curve x equals 2 sine t, which is defined parametrically here, and y is equal to sine 2t. And I've specified the domain exactly as it was in the question. So it's in decimal form, but that's from pi over 2 up to 3 pi over 2. So you can see this confirmation. The domain goes from -2 up to 2, and the range runs from -1 up to 1. Okay, so that's where the minima and maximum are respectively. So you get this curved shape reminiscent of a trig function. Now I've also got the Cartesian form here. Now I'm just going to show you the rationale. If I take the negative branch, which we argued was the correct branch, and I just click on this to show it, you may have noticed, I don't know if you can, that it just overlaid. I'll take it off again. It goes green, of course. It overlays exactly with the parametric form for that specified range of values of t. Now, if I'd have done this wrong, if I'd have taken the positive branch, you can probably tell what may happen. So I'm going to put that on. So the positive branch completes the circuit, essentially. So you get this rather nice sort of bow tie shape. So I just wanted to show you this just to confirm that the maths and the graphing does in fact correspond together. Okay, so our final example in this section is example 5, and we're going to utilize some of the results we found in the warm-up earlier. The main one being this result here, where we have the sign of t subtract pi over 4, which I was just trying to highlight then. Okay, so we have to find just the Cartesian equation of the curve. Okay, so we don't need to worry about anything else in this particular example. So let's start with equation 1, which I haven't labeled yet. So we'll call this one equation 1, of course, and y is equation 2. And we'll apply our identities, the compound angle identities that we talked about in the warm-up. So we're going to use sine of a subtract b is identical to sine a cos b subtract cos a sine b. Now we did all the work earlier. I'll just fill it in again. Remember, of course, that a corresponds to t and b corresponds to pi over 4. So in this context, we've got a slightly different x setup here. So we have that x is equal to root 2 over 2. And we're going to use the right-hand side of this identity now. And we'll just plug in our t and our pi over 4. Okay, and we'll see what happens. So again, just look at the warm-up again if you're not sure what's going on. So it's going to be sine t cos pi over 4. And we'll evaluate these in a moment. Subtract cos t sine pi over 4. Like that. And I'll just put a green bracket just to be consistent. Okay, so I'll put that in big square brackets because in this instance, we're multiplying the whole thing by root 2 over 2. Let's find out what those constants are. Again, we did those earlier. So we've got x is equal to root 2 over 2. And big square brackets again. What do we have in here? Well, cos of pi over 4, we deduced that was root 2 over 2 as well. So that's good. Let's just fill it all in. So that's going to be root 2 over 2 sine t subtract, and again, sine of pi over 4 is exactly the same, root 2 over 2 cos t. Close your big square brackets, and we can multiply through by root 2 over 2. Now, when we do that, there might be a little bit of simplifying we can do here in a moment. Root 2 multiplied by itself just gives us, of course, 2. So we'll have 2 over 4 multiplying the denominators, sine of t, subtract exactly the same thing, 2 over 4 cos t. Now, obviously, 2 over 4 is just going to simplify to a half. So therefore, we're going to have x is equal to 1/2 sine t subtract 1/2 cos t. Right. So you can just pause there for a second. Right, where are we up to? Well, we've broken down our equation 1. We've got an expression for cos t that's given to us by equation 2 up here. So I know I can replace my cos t with y. So that's good. That's getting me well on the way to getting a Cartesian form. The problem is we've got the sine t sat here, which we have nothing to substitute in for at the moment. Well, let's just make it a little bit more simple. I'm just going to move up to the right-hand side here, and we'll see what we can do with the sine t. So have a think about that if you're not sure what to do. Maybe pause the video, see if you can do it yourself. But the first thing, I'm just going to multiply everything by 2 to clear that fraction. So therefore, we're going to have 2x is equal to sine t subtract cos t. And what I will do now is I can now replace the cos t with y. So given that y is equal to cos t, we now have that 2x is equal to sine of t subtract y. Okay. Now then, looks like I'm getting towards a Cartesian equation. But if you think back to what we did in the earlier examples, a good method initially is to make the sine t or the cos t or whatever it is the subject of your equation. And we can actually do that here. If I add y to both sides, you'll notice that I'll get the following. I'll get 2x plus y by adding y to both sides is equal to sine t. Okay, so we know that, and we also know that y is equal to cos t. So we're now in the situation after just doing a bit more algebraic manipulation here, that we need if we had an identity that linked together sine t and cos t together and nothing else, we could get a Cartesian equation. And yes, we can do that. We've used it several times. So we're going to use sine squared t plus cos squared t is identical to 1. And if I do that, I just have to square the sine, square the cosine, and add them together and set them equal to 1. And we've got our Cartesian equation. So if I square the sine, that's going to be 2x plus y all squared plus y squared is equal to 1. And note that we're given a form in which to write it, and we seem to have it straight away. And if you weren't sure what to do, notice there is a little bit of a clue in how it's presented. You've got a squared term here, a squared term here equal to 1. It suggests using one of those Pythagorean identities. And furthermore, we've got the a coefficient here corresponding to 2. So we can just write that down. So a is equal to 2. So that's our Cartesian form. Again, no domain or range to worry about here, but we've done quite a bit of manipulation, used some identities, and we've now got an equation purely in terms of x and y as required.